Hello, and thank you for dialing into our webinar today. Yeah, so we give a short introduction of ourselves so you know who is presenting today. Milan, do you want to go first?
Sure. So, hello, also welcome from my side. I'm Milan, cybersecurity engineer at ITK Engineering. Yeah, from a background, I have a PhD in the area of cybersecurity and also several years of experience in the field. And in my current role, I'm basically consulting our automotive OEMs on cybersecurity processes and especially focus on the topics of performing risk analysis and doing security concepts.
Okay, perfect. Yeah, my name is Lena Steden. I have been with ETAS for some time, and I have done a lot of work in the area of risk assessment and risk management. And currently I'm our service lead, so responsible for our security engineering services. And I'm also supporting ETAS as a lead technology officer for security risk analysis. And apart from ourselves, I would also like to give an introduction to what you can expect from today's webinar. We have a short overview of why threat analysis and risk assessment, so TARAs, are relevant, especially in the context of the UN Regulation 155. And I would like to give you some insight into the current situation in the industry with that for this topic. And then we will get straight to a live demonstration of our new tool, SecuRisk, and Milan is going to do that presentation. And then as announced, in the end, you will have time to ask questions, and we give our best to answer them. So let's start right out with the relevance, so why we are here. So if you have signed up, you have some motivation why you should do TARAs, and one more or less recent development in the industry has been that the UN Regulation 155 has become effective for new vehicle types last summer, and it has, so if we have a closer look at that regulation, you can see that it falls into two core requirements. The one illustrated on the left-hand side is that you have to operate and certify a cybersecurity management system, CSMS, in your company. And then the second requirement is that you do not only have to have the CSMS on paper, but you actually have to apply it to the development of your vehicle types. And that has different technical implications and implications on project level. And with our focus on risk management today, we have a special focus in that second discipline, so securing vehicles by design to mitigate risks along the value chain. And that discipline is mainly covered by the two requirements that you see on the screen. They are actually taken from the regulation, and the requirement 733 tells us that you have to identify all the critical elements of your vehicle type and then do exhaustive risk assessment for that. And of course, not only identify the risks, but also treat and manage the risks appropriately. And for those steps, threat analysis and risk assessment is the appropriate measure to do it, or the method to do it. So here we have a strong motivation from a regulational point of view. If the internal motivation to provide secure and safe products and vehicles to the market is not enough, then you have that motivation from the clear motivation from the UN regulation and for the type approval as well. If we have a look at what is going on in the industry, we get a lot of feedback from our consulting projects that we have with automotive OEMs and suppliers, but to get an even better understanding and to actually get numbers and not just feelings and impressions, we have done a survey in the industry together with our partner KPMG. And last year we had over 160 companies in the top automotive markets like China, US, or India participating. Of course, we also had participants from Europe in there, and the results have recently been published in a white paper that you can find on the ITAS website. So if you're interested in the numbers, the figures, and also the conclusions that we and KPMG draw from those numbers, you can find the white paper on the website. And in the survey, we have asked 20 questions in 4 different parts or topics to the people, and it was a self-assessment style of survey. The survey took place approximately a year ago, and we are already looking forward to the next round of the survey this year. And I'm curious to see how the numbers have evolved and how the industry got more mature in terms of cybersecurity. For today, I picked out 2 questions from that third part, which is titled Risk Management and Supply Chain Management. I think that's interesting also with respect to threat analysis and risk assessment. And let's have a look at those 2 questions that I picked. The one is, how does the organization implement risk management? And it's interesting to see that around like 2/3 of the participants say that they have at least established processes for risk management, which is good. But it's also interesting to see that only 9% each have answered that they are already applying automated tools or even regularly updated or automatically updated threat databases. So we see that a lot of growth can be in exactly those areas. So people have understood that they need to do risk management and that they need to do it in a defined way. And the UN regulation and the ISO 21434 give us good guidance and requirements to do that. But it can get even more mature, more efficient to do those risk management tasks. And the second question that I picked is, on what levels does the organization perform their risk management? And that is a spread out answer, but we were surprised to see that the answers for risk management, risk assessment on item level or product level is rather low, although those terms are explicitly mentioned in the UN regulation and in the ISO 21434 that you have to do risk management on exactly those levels. Maybe it's a question of definition, because for component and function level, the numbers were much higher, and it was a self-assessment, so there was little to no additional explanation to the terms and definitions. So maybe that's a wording thing. The lowest number here is that risk management is done also on enterprise level, and this will be the next challenge to connect different areas and silos in the organization to do risk management end-to-end for the vehicle value chain. And exactly this point takes us to 3 challenges that we see from the survey, but also from our experience in customer projects that we have done over the past years. So one challenge, and that's maybe also the first challenge from many companies, is that they update their legacy methodologies. So companies have had methods and processes to do risk management even before the regulation and the standards came into place, and now they update their tools, templates, knowledge management to the requirements and that we have now for the industry. The second challenge is to do risk management in a joint way between suppliers and customers. So the organizations have discovered that they are not independent, but they have dependencies with suppliers, customers in their production chain, and they have to rely on them also in terms of information about risks, threats, and impacts for cybersecurity. And it's a challenge to balance what kind of information do I want and have to share, and what information do I have to protect because it's intellectual property, for example. And in that area, it is difficult to have common terms and interfaces between different methodologies that are present in different companies, because even if you fulfill the regulations and standards and all the requirements, you can still come up with different, also valid interpretations there. And the third challenge that we see is what I already hinted at with the last question that I had on the slide, is that you have to connect at one point the results from the more technical development-based risk management in the projects to the corporate risk management. So at one point in time, the technical cybersecurity risks have to become business risks related to legal or financial risks for the company. And here we have really two different ways of thinking, ways of working, talking that have to come together. So the technical side and the business side, and that's a challenging task to align those methods and understandings for the for risks and threats. So those are the observations that we have in the market, and from all of that, we have learned, and many of our customers have understood that it is not feasible to go on with the maybe proprietary tools that they had in the beginning, but it's time for a next level tool that supports you more with those processes and challenges. So let's have a look at where we are coming from. So we have done TARAS for many years for the automotive industry, but as many of you, we have also been using huge magical Excel sheets. We have done reports in Word because everyone is familiar in Word, or use LaTeX because it has some nice automation features already. But with new requirements, with more and more TARAS that you have to do and that you have to update, we came to the conclusion that it's time for more modern tool, and that is how we came to our new product, SecuRisk. We did not develop the SecuRisk on our own, but it has been developed by and with the Bosch mobility branch and ITK Engineering, and that is also why Milan is around to tell us more about the tool in a minute. So I have an overview of the main features, but we will see them also in the tool, and I see that it's much more telling if we see how it works actually in the SecuRisk tool. So it supports you, the tool supports you with creating TARAs that are fully compliant with the ISO 21434. And of course, it comes with those things that you need to do a TARA, like an integrated and really usable attack tree editor. It supports the automatic calculation of attack potentials. And one feature that you will see and that I like from my consulting point of view is the automated management summary, which allows you to compare different variants of the system to really see what is the impact if I choose or do not choose a certain mitigation, for example. And that can be a really helpful feature there. Regarding the way of working, the tool comes with an integrated review functionality, so you can directly comment in the tool on anything that you or your colleagues have done, and there's no need to do an export first and do comments on PDF and then go back to the tool or something. You can do it directly in the tool. And regarding the style of the tool, so the tool comes as a client-server version, and our approach is that the server is hosted on-premise, so within your network, and it is a feature for you to keep your critical data under control, so you know exactly what policies and what restrictions you want to apply to this data, and there will be no data on our server or on Bosch servers or wherever, so there's no need to worry there. And as I already said in the introduction, although the tool is now new on the external market, the tool has been used within the Bosch group for about 2 years, and they have done hundreds of TARAs and also done complex development projects with more than so with 50 and more ECUs in a vehicle, for example. So Bosch is actually using the tool in their everyday life for their in their project development. So it is well tested, and our experience and their practical experience with the tool also feeds back to updates and improvements that we are doing to the tool. So that is the rough overview of the features, and now we have Milan, who gives us a demonstration of the tool, so you can have a look at how the tool looks and what a user-friendly GUI could look like.
Thank you, Lena. I will share my screen in a second, briefly give an introduction. So as I mentioned, I'm a cybersecurity engineer, and in this role, I'm supporting our customers in setting up the required processes and doing risk analysis and security concepts. And as Lena already mentioned, in the next roughly half an hour, I want to give you a glimpse in our daily work by showcasing the CycleRisk risk analysis tool and demonstrate how it supports us in doing projects with our customers. And I will start by showing how we can set up a new TARA project using the tool and how quickly we can model a given system from a cybersecurity perspective. This part will show the tool's more basic functionality, which you might also expect from other tools out there. But after this, I will also show some real-world challenges that we have encountered in our project work. For example, this includes support for platform products, so products that are to be offered in different variants. These can be individual components or subsystems, but also entire vehicles that contain a complete INI architecture. And also I will talk about how the tool allows us to treat the risk analysis really as a living document, and thereby enables us to assess risks during the entire product lifecycle. But before I will now show you the user interface of the tool, I want to make a short disclaimer. The examples that we have prepared for today have been rather greatly simplified for the purpose of this demo. but also, of course, we do not want to violate any of our customers' IP. So please don't take these examples as a blueprint for what we consider a complete and in-depth risk analysis that we would normally do for a customer project. So the tool that you're seeing today is the internal version that we're currently using. It's not the same. It's the same version that you will find on the market. So there will be some rebranding done, but the functionality will remain the same. So let's get started. What you can see on the left side, we have a menu bar, and in the first item is the project cockpit, where we can put in some metadata about the project, of course, project name. We can also edit the project history a bit. So once the document is reviewed or released, this can be all modeled in the project itself. Then directly the second part is what we call the TOE description, the target of evaluation. And this will typically contain information about the system or item or component that we want to analyze. And for the purpose of this demo, we have prepared a very rather simple headlamp system, which you can see here highlighted in blue. It mainly consists of a body control ECU that has a switch connected to it. So the user can basically control the headlamps. And the body control ECU is also connected to a CAN bus, which in turn is also connected to the power switch actuator, which is wired to the actual headlamps. And this power switch actuator reacts on some CAN messages. So we have this lamp request here that can request to set the headlamp to off, low, or high beam. And yeah, that's basically the item that we want to consider today. Of course, we always have to consider also the operational environment. And here we assume that there will be at least one system that is also connected to the same CAN bus that can provide information about oncoming traffic. So we have a CAN message called oncoming car information that has a Boolean yes or no. For example, that can be sent from a camera ECU, and that will also be interpreted by the power switch actuator. That's not all. We also assume that there will be some sort of gateway ECU also connected to the CAN bus, and this gateway ECU will have an OBD port. Why? Because, well, at some point we might want to update our body control ECU, and we need a way to update its firmware. You can also see two optional components in the operational environment. So we have a TCU here with telematics capabilities because our product team said that our headlamp system should support firmware over the air updates in the future. Not in the first version, but maybe later on with a software update. This should come in. So this is why I marked this as optional. And then also we have this tire pressure monitoring system here, which is also optional, which will become important later on in the demo. All right. So this is the system that we will be looking at throughout the demo today. And now we will look at the basic functionality of the tool that you might expect from any other tool which supports TARAS following the ISO SAE 21434. However, what is a bit different in the tools, and I think that's pretty cool, is that you can configure the complete methodology, including impact categories and so on. So we can, or you can tailor it to your organization's need or needs. So the first section that you might be familiar with, if you know the 21434 or have ever done a risk analysis, is the damage scenarios. And of course, we can add new damage scenarios. They basically encode what can go wrong in your system. So for example, for this headlamp system, the headlamp does not turn on. Could be a damage scenario. And then, of course, we can set the impact ratings on different categories. So we, of course, support the categories required by the 21434. So we have the safety impact on the road user, for which I just set some random value. Financial impact, operational impact, privacy impact. But as I already mentioned, the tool also supports configuring the methodology. So if you have already existing methodology implemented in your company, you can tailor the tool to fit or to basically match the methodology that you're already using. So here, for example, we added 2 more categories with impact on the organization. All right, next, what we can or what we need to do is we need to define some assets. So these are the components in the system that we deem worth protecting. So this can be, for example, the body control ECU. And then we need to assign some security properties. In this case, we might only be interested in the integrity of the ECU. But of course, our system also has other assets, not only ECUs, but we also have CAN messages, which can be modeled as an asset. So let's take, for example, the LAMP request that we have seen before. And here also, we are interested in the integrity of the request, but maybe also we're also interested in the availability. Why? Because when blocking a LAMP request, then our headlamps might not turn on or turn off, depending on what the request contained. So availability might also be of interest. Next, we can head over to the section threats. And you can see it's already pre-filled. And this is not something that I have prepared ahead of time, but that was just auto-generated by the tool when I defined the assets and their security properties. So you can see that threat number 3 is called blocking of LAMP request, and this is basically generated from the asset LAMP request and the security property availability. And what we need to do next is we need to assign some actual damage scenarios to the threats. So the threat basically encodes a violation of a security property of an asset, and that might lead to some damage scenario. And conveniently, I've just created a damage scenario that might fit here. So if a LAMP request is blocked, then this might lead to the headlamp not turning on. So we can assign or link this damage scenario to this particular threat. And then usually we would do this for all the damage scenarios and all the threats that we have identified. And we'll end up with a list of threat scenarios. And these threat scenarios, you're also familiar already, come from the 21434, and these encode our actual risks that we have in the system. And you know, a risk always consists of an impact rating and an attack feasibility rating. The impact rating we get from the damage scenario, and the attack feasibility rating or the attack probability we get from the corresponding threat. All right, and now the question is, how do we get to the attack feasibility rating? And the 21434 offers some options on how to come up with these ratings. We have found that the most accurate and efficient way to do this is via attack trees, because they allow us to very efficiently and concisely summarize a lot of different attack paths that we have. So this is also what the tool supports. So we can model attack trees, and what you can see is that for every threat that has been defined, we get a corresponding attack tree template that needs to be filled. And then now let's go into the attack tree modeling view. We can see that we have an empty root node here. And now we can start filling it by adding additional nodes to this. One node type that the tool supports are so-called intermediate nodes that by themselves don't have any attack feasibility rating, but rather indicate how their child nodes should be combined. So they can either have a logical AND or a logical OR connection. I will explain in a bit what the difference is. And then finally, at some point, we need to define some attack leaves. And then these attack leaves will have the attack potential ratings that we already know from the 21.44. We use here the same ratings as we find in the standard. But again, also this attack potential methodology can be adjusted to your organization's needs. All right, maybe just let's add another attack leaf to make clear what the difference between an or an AND node is. As you can see, an OR node means that in order to realize the node or the threat, only one of the child nodes need to be realized. So the algorithm here takes the easiest attack path and propagates it to the top. It indicates this by highlighting the critical path in orange here. And what is also worth mentioning that we can see two ratings up here on the left side, and on the right side it has the same attack feasibility rating. That is because the tool has native support for doing a residual risk analysis. So once we have implemented our security concepts and implemented our security controls, we want to make sure that our attack feasibility, that they are effective and that our attack feasibility levels will go down. So currently, since we have not defined any security controls, both ratings are exactly the same. All right, just to show you what this OR and AND connection means, let's switch this to AND. AND means that all the child nodes need to be fulfilled in order to realize the threat. So you see that basically now the lowest rating is propagated up to the top node. Yeah, and we can use this to model attacks that require a number of different steps or that can be realized by choosing different attack paths. Right, one more really cool thing about the tool's attack tree support is what we call technical attack trees. Technical attack trees are basically reusable attack tree branches. So when we did Taras for our customers, we realized that, especially when we do complex ones, we realized that we would redo the same attack tree branches in different attack trees. So we had to do a lot of redundant work to model the different attack paths. So this is where the idea of technical attack trees came from. So the idea here is to encapsulate certain attack paths in a dedicated subtree that can be reused across different attack trees. How can we do this in the tool? We can either build them explicitly, or if we have already been working on the Tara for some time and realize now that this particular branch we would need in a different attack tree as well. We don't have to remodel this, but we can just right click and say extract as technical attack tree. And when I do this, the node that you just saw has been replaced with a new technical attack tree that, if we expand it, will contain the same attack leaves as before. And now, of course, what we can do is we can go to a different, or edit a different attack tree and use the exact same technical attack tree again. So this is extremely efficient and time-saving feature. Of course, now if we other advantages is that now, if we need to modify one of the technical attack trees because we realized, okay, we missed a certain attack path or we found a new vulnerability in the system, we can just go to the technical attack tree, add a new node here or a new branch here, and then the results will be propagated. Will of course be propagated to all the other attack trees where this technical attack tree is being used. All right. So, and now this Tara so far does not look very impressive. And now I'm going to do what every good cooking show has been doing for the past decades, is that I will pull out the oven a completed or more complete Tara. So this is now fresh out of the oven. We have still considering the same system, but in the meanwhile, we have been adding some more damage scenarios. We have been adding a new asset, also have a new number of threat scenarios. And last but not least, also our attack trees have grown. So that's great. Let me show you briefly what they look like now, because this will become important later. So of course you can collapse the child nodes of these trees to make them a bit more accessible. What I just want to show you here is the 3 different attack vectors that we considered for the manipulation of the body control ECU. On the left side, we have flashing a malicious firmware. So an attacker basically builds a malicious firmware and is able to flash it to the component to gain control. Of course, this now contains a number of attack steps that we need to realize. The second path is via identifying and exploiting a vulnerability in the firmware. And last but not least, and this is maybe not completely intuitive, is an attack via a downgrade of a firmware, where we assume that the attacker gets hold of an older version of the firmware for this ECU, is able to flash it on the ECU, and then exploit a known vulnerability on it. All right. And so this is what I wanted to show you. And now our Tara is sort of complete. So we have all the damage scenarios, we have our attack trees. Now we want to have a look at our risks in our system. And this is where the management summary can come in handy, because it provides an overview of the risks that we now have identified. There's 2 different views. We have a summary based on the impact category up here, for both the initial risk and the residual risk analysis. Recall, we don't have implemented any security controls, so the ratings are still the same. And then the other view is based on the well-known risk matrices, where we have the impact rating on the x-axis and the attack feasibility rating on the y-axis. All right, and now what we would to do is we will need to do a risk treatment decision for each of our risks that we have in the system. And of course, the tool also gives you a list of the risks that have been identified. And then together with the decision makers, we will need to decide whether we want to retain, reduce, or share the risk. If we decide to reduce the risk, we also have the option to define a security goal. That will be the input or one input to our security concept. So I will not do this now. I'm just going to assume that we will do this for all the risks that we have. And then with our security goals and our security claims, our cybersecurity engineers will come up with a very cool security concept for the headlamp system. And once we have the concept, we can circle back to the Tara and do our residual risk analysis. And for this, what we will do is we will implement a number of security controls that we can do here. And for each security control that we define, the tool automatically will create a special type of tree that we call circumvent tree. And that can be attached to our existing attack trees. And they're intended to increase the complexity to realize a certain attack path. Here, I'm not going to go into detail. I just want to show you, I'll give you an overview of how this works. So let's go back to our management summary. And what we can do now is we can expand the security controls section down here and start activating, for example, secure flashing. Secure flashing, why? Because, well, of course, we want to protect the integrity of the body control ECU. How we do this, of course, via secure flashing. So let's activate this. And we realize that nothing happens. Okay, so why is that the case? Let's go to our attack trees again. So we can have a look at the attack tree for the manipulation of the body control ECU. And we can see that, yes, we have this branch for flashing and malicious firmware here, which would be protected by our secure flashing mechanism. But actually, our critical path at the moment is the path via the downgrade attack. So we will definitely need to add another security control which implements downgrade protection. And now if we activate this, we can see that at least some of our risks actually dropped from the criticality level. So that's good. That shows that or validates that the security control is working. And let's complete this. We have another critical risk here that is realized by the manipulation of the LAMP request. So let's add another control for authentication of this LAMP request. And once we activate this as well, also our remaining critical risks have been mitigated. Great. So now we have done the Tara by the book. But as we know from several of our projects, we are often faced with non-standard challenges as well. And in this second part of the demo, I want to highlight some of those challenges and discuss how we can tackle them efficiently with support from the tool. The first challenge is that most of the time, what you've seen so far, doing an initial and a residual risk analysis are just not enough in practice. But we usually need more configurations that we need to compare against each other. And the second one is that we might need to support different variants of the same system. And I will show you how we can deal with those two challenges right now. So we have seen that that we have this TCU in the. Sorry, I'm going to show you. We have the TCU connected to the gateway. And now the question is, what happens if we enable photo updates for the body control ECU? And the way that we can go about this is via what we call toe configurations. So configurations of the target of evaluation. And these can be thought of as sort of tags that can be attached to basically any artifact in the Tara. So it can be an asset, it can be a threat, it can be an attack tree or just a branch of an attack tree, it doesn't matter. So you can basically attach such a tag to any of these artifacts. And then once you activate them, these artifacts will become active. They will be included when you run the analysis, or when you deactivate it, it will be excluded from the analysis. So that's pretty handy and really powerful tool to be able to implement different variants. And now let's go back to the management summary. We can do this from here. Let's add another configuration, which we will call FOTA, and where we activate just this one tow configuration. And what we can see is that once we activate FOTA updates, our risks don't change. So that's good. So we can make the statement that yes, we can add FOTA updates to the system without compromising the security of our system, or at least we don't increase our existing risks. And now we can actually start playing around a bit if we want to know what the impact of our secure flashing is. If we deactivate this, we can see that suddenly our risks go up again. So this is also an important message that we can tell to the decision makers, saying that if we want to have FOTA updates, we definitely also need secure flashing, because otherwise it will just blow up in our face. All right. Now let's think of a different story that we also have encountered a couple of times. Is while doing the Tara, we are working with a preliminary architecture of the system. So the system is still being developed, and at some point in time, the system architect comes to us with a great idea, saying that, well, we want to add a tire pressure monitoring system to this CAN bus for performance or cost reasons or whatever. And basically asked us, what is the impact on the security of the system? And well, usually what we need to do if we didn't have this feature is we would fork this Tara project, integrate this TPMS system, and reevaluate our risks. But with SecuRisk, again, we can just simply create a new tow configuration, extend our attack trees, and then basically toggle the switch. Now let's say this is no longer called FOTA, but TPMS, and we activate the tow configuration for the tire pressure monitoring system. And again, we can make a statement backed up by the Tara in a very short time, actually, where we can say, yes, we see that there are some risks that increase a bit, but our risks don't become critical. So that's important information to the decision maker that we can give to them on short notice as well. Yeah, so that's great. So now we have done our Tara. Tara is complete. And as you know, at some point we want to release it. And before we release it, we need to do a review. And doing a manual review of a large Tara can be quite a time-consuming process. And as Dana already said, we have a review. We have a review support for the Tara in the tool, but we also have an automated functionality, which we call validation. And with this validation, the tool uses a fixed set of rules to formally check our current Tara project. And we have 3 different severity levels. We have informational messages that can be, for example, we have 2 assets with the same name or with the same description, which would hint at we have a duplicate asset there. So the analyst can go back and check whether this is actually a problem. We can have more severe warnings where we're missing the reasoning why a certain threat scenario exists. And this can become critical if we want to do an audit, because the auditor might not understand why this threat scenario exists and why it has been rated in this way. And we also can have errors, something like we have an empty attack tree node, which typically means that we have forgotten to add something to our trees. So this, of course, doesn't replace a manual review, but at least it helps us in doing so. All right, so now we have released the Tara. Our system is being designed, it's being implemented. We do the full V-cycle, testing, production, and now the product is in the field. But as we all know, is that our security work does not stop there. Right? So we might be faced with new threats while the system is in the field. For example, let's assume that our vulnerability monitoring system discovered a severe vulnerability, or a security researcher detected a new vulnerability in our body control ECU. And now our incident response team received this report and obviously needs to decide how to deal with this. And to make an informed decision, they would come to the cybersecurity engineer and ask them, look, we have received this report over here. Our body control ECU is vulnerable to an arbitrary code execution exploit that can be realized with access to the CAN bus. Can you please tell us what is the impact on the system? And of course, we can help. How can we do this? I would typically go back to our attack trees, select the one that matches, that corresponds to the report that we have just received. Then I would first of all look whether we have an attack tree branch that corresponds to this new exploit. And in fact, we have the middle one that is also currently our critical path, which is called Identify and Exploit a Vulnerability. And now let's have a look, more detailed look in what is in there. So in the model, we said in order to realize this path, we first of all need to have access to the CAN bus. Then the attacker needs to identify an exploit or a vulnerability that is exploitable, and then they need to also prepare the exploit. And if we closely look at this, there's actually an implicit assumption hidden here. And the implicit assumption is that the body control ECU does not have known vulnerabilities in it. So let's make this explicit. All right, so let's say body control ECU has no known vulnerabilities. And let's go back to our attack trees. And what we can do now is that this attack leaf here, the identify a exploitable vulnerability, is actually tied to this assumption here, right? Because we only need, or the attacker only needs to invest into that step if they don't already have a known exploit. And now, since we have received this report from the security researcher, and this is, we have to assume that this is now public knowledge, this assumption no longer holds. And now the question is, what is the impact on our system if this assumption no longer holds? And let's go back to our management summary, where we say body control ECU is vulnerable. We deactivate the toe configurations, and we can expand our assumptions here. And these assumptions work in a very similar way to our toe configurations, in that if we deactivate the assumption, then the corresponding artifact is excluded from the analysis. So if we deactivate this, we see that our risks go through the roof again. So we can, again, give the feedback that yes, we definitely need to fix this. All right. And now looking also at the time, I think I'm done with my demo for today. I thank you a lot for your attention.